Hey guys, and welcome to a video tutorial about capacitors. Now, capacitors are very useful in terms of circuits. Capacitors can be something as simple as two metal plates, and you have current flowing through, and you've got this connected to, let's just say, some form of potential difference. We'll call that VB, just some voltage like a battery or something like that. And what happens is, with a capacitor, this is a parallel plate capacitor, very cleverly drawn as two parallel plates. Now, what happens on one side or one plate, you will induce a charge positive Q. Now, you've got some non-conductor in between. So sometimes this can be something as simple as a vacuum or air or something. Then you induce a charge over here on this plate of negative Q. Now, capacitors all have a certain capacitance. And so capacitance is basically the ratio of charge induced on a plate divided by the potential difference of a capacitor. I'll call that VC. So, capacitance and charge and potential difference. How does that help us out? Well, in between those two parallel plates, there is an electric field. And if you look, over here I've got positive charge all along this plate. So my electric field would be fleeing from that towards the negative. So I've got an electric field that looks something like that. Now, electric field, a very useful equation for it. Electric field is your change in voltage over your distance. So these plates are a certain distance apart. They've got a certain amount of separation going on between the two. Now, what about capacitance? Well, another useful equation for capacitance relates the distance between the two plates and the area of the two plates. So, another equation for capacitance. You can have epsilon naught times A, the surface area of a plate, divided by the distance between those two plates. And if you look, as the area of your plate gets larger, you have a greater capacitance. If the separation between your two plates gets smaller, in other words, you bring those two plates closer and closer and closer together, your capacitance also increases. So capacitance and distance between the two plates are inversely related, and capacitance and area are directly related. Now, if you look over here, I've got another equation for capacitance as Q over VC. Q over my voltage difference, or the potential difference between those two plates. So let's take that and combine the two equations. So a quick rundown. I've got capacitance equal to Q over the potential difference across the capacitor. That looks bad. VC. Then I've got electric field as equal to my voltage over distance. Then I've got capacitance being equal to epsilon naught times area over D. So here's what I'm going to do. I'm going to take this equation and I'm going to plug it in here for C. Well, that gives me the charge on a capacitor divided by the voltage across that capacitor is equal to epsilon naught times area divided by distance. Now, this VC, this potential across the capacitor, if you look, I've got that VC kind of right here. If I make the D the distance across that entire capacitor, well, that's going to be the voltage across the entire capacitor. So let's rearrange this and let's get VC out of this equation. So multiply both sides by D. I would get VC being equal to the electric field times my distance. I can take that and plug it into this equation. So Q over my electric field times my distance is equal to epsilon naught times my area all divided by my distance. Now, if you look on both sides, I have distance, which cancels out. giving me Q over E is equal to epsilon naught times area. So if I wanted to isolate Q or isolate E, I could flip both sides. There's a lot of different things that I could do, but I would end up with another equation relating electric field to the charge on a particular capacitor. So very important relationships that are good to know. The capacitance is Q over the potential difference. The electric field is the potential difference divided by my distance. The potential is equal to electric field times distance, which this is basically a rearrangement of that equation. Now, how do capacitors work in a circuit? Well, in a circuit, we're going to have some symbols that we need to talk about. So, let's say that I've got two capacitors in series with each other and they're connected to some battery. So this is the symbol for a battery. You've got a long line and a short line. The long line represents your positive terminal. Your short line represents your negative terminal. And let's say this battery is a 9-volt battery. Now, let's say that I have a capacitor here, and let's say it has a capacitance of 2F, or 2 farads. So this is my capacitance. Let's say this capacitor has a capacitance of 4F. Oftentimes it's useful for us to figure out what is the equivalent capacitance. So here's what we're going to do. These two capacitors are in series with each other. Here's what this means. When something is in series, there's only one way for the current to flow. So in this circuit, we have current. And we always draw current flowing out of the positive terminal of our battery. This is conventional current flow. So current is flowing out of here. Current flows into that capacitor, and then back to my battery. Okay, for something to be in series, there can only be one path that current can take. So the current has to go in there, has to come out there, and then go back into that capacitor. So those two are in series with each other. To get what's called the equivalent capacitance, in other words, we're going to combine this and make it as if it were one capacitor. The equivalent capacitance for capacitors that are in series, it is 1 over C1 plus 1 over C2. That equals 1 over my equivalent capacitance. That is your equation for equivalent capacitance when you have capacitors in series with each other. So this circuit would basically be 1 over 2 plus 1 over 4. So we got 1/2 plus 1/4. Well, that's going to be 3/4 equal to my equivalent capacitance. Well, I reciprocate both sides, and my equivalent capacitance for this circuit is going to be 4 over 3 farads. Now, why is that useful to us? Well, a lot of times we might be asked to figure out, well, what's the charge on a particular capacitor, or what is the current or voltage across a particular capacitor. Well, things in series are going to have the same charge. So each of these capacitors are going to have the same charge on a particular plate. Okay? Now, to get that charge, we know the equivalent capacitance. That's what we're going to use to figure out the charge on each of those. So, very important. Capacitors that are in series have the same charge. And so here's what we're going to do. I know that capacitance is Q over V. So I know the equivalent capacitance. Now, I don't know the charge on each capacitor, but I know the voltage across the entire circuit. If we look back, our voltage is 9 volts. which means it's kind of like I start with 9 volts, I have to end with 9 volts. So our voltage across the entire battery is 9 volts. So that's what we use for here. I'll call that VB, the voltage of the battery. So our C equivalent was 4 over 3. That equals Q over the voltage of the battery, which was 9. Multiply both sides by 9. 6 times 4, that gives me Q equal to 24. Now, that Q is the charge on each of my plates. So here I have plus 24, minus 24, plus 24, minus 24. So since they're in series, they have the same charge. But each one had a different capacitance. This one had a capacitance of 2 farads. This one had a capacitance of 4 farads, which means they have the same charge but different voltage. And to get that voltage, well, now we know the charge on each capacitor. We can use C equal to Q over V. And we can use C1 to figure out V1, and then use C2 to figure out V2. So that's for capacitors in series with each other. But what if we have capacitors that aren't in series but are in parallel with each other? Ooh. So here's my battery, plus minus. There's 9, and we'll say this is again C1 and C2. And let's say it's the same 2 capacitors. So I've got C1 equal to 2 farads, and then C2 equal to 4 farads. Okay. Now the capacitors are in parallel with each other. Now, here's how you know they're in parallel. I have the current flowing out of my positive terminal, but now the current can flow and will flow through that capacitor and through that capacitor. It has an option. It doesn't have to flow through this one and then go to the next one. So it can flow through both. And if you look, they're in parallel with each other. So for parallel capacitors, this is super easy. To get your equivalent capacitance, all you do is you add the 2 capacitors together, or however many capacitors that you have in the circuit. So for here, my equivalent capacitance is just going to be 2 plus 4, which would be 6 farads. So when I do this, I basically make this one capacitor. Now I can use that equivalent capacitance, and I can solve for that. Now, things that are in parallel. So, capacitors that are in parallel have the same voltage, which should send off a red light. If they have the same voltage, they will have different charge. Okay, so you figured out, or we figured out, the equivalent capacitance. Well, we know the voltage across each of those capacitors. It's going to be 9 volts. Because again, if you think about our battery, we made that one capacitor. Well, here's 9 volts, so think about it like I start with 9 volts. Well, this thing also has to have 9 volts. That's my equivalent capacitor, which means each of my capacitors, C1, it has a voltage V1, which is 9 volts. C2 has a voltage that is also 9 volts. Parallel, same voltage. Now, we have the capacitance and we have the voltage. We can solve for the charge on each because they have different charges built up. So, that's a quick rundown of capacitors that are in series and are in parallel.